So we've got a polynomial time approximation scheme for Knapsack. The problem is, of course, like I said before, the time complexity is exponential in k. So we have this big O of k, n to the k time complexity. And so if we wanted to get very close to the optimal, we would have to make k very large, and that's going to cause problems. Exponential in k. And so, like, think about this. What if we want our approximation factor to be 3/2? Right? So here's our approx ratio. So this is 1.5. So this requires us to have a k of 2 equals 2 or so. Okay, 2 or 3. And so this gives us n squared. And so now if we wanted 5/4, this requires our k to be 4. And that gives us n to the 4th. What if we wanted to come within 1% of the optimal? Well, that says our approximation ratio is 101 divided by 100, and this means our k has to be equal to 100, which leads to an n to the 100 factor, right? Which is not a good thing, right? These are quite large numbers. And so we want to ask, can we do better, right? Is this the best we can do? And the answer is no. So it turns out there's a refinement of this concept, the concept of a polynomial time approximation scheme, called a fully polynomial approximation scheme. So a fully polynomial approximation scheme is one where the running time of the algorithm, well, first it's an approximation scheme, so you have an error parameter that you can tune to get you close to optimal, and the running time is polynomial in n, and also in 1 over epsilon, 1 over the error term. So here's our definition of a fully polynomial time approximation scheme. Fully polynomial time approximation scheme, or FPTAS. Is polynomial in n and 1 over epsilon. I'm not going to write the full detailed definition, but this will give you the idea. So polynomial in n and in 1 over epsilon. And so our fact that we'll kind of close this video with is that the Knapsack problem has a fully polynomial time approximation scheme. So Knapsack has a FPTAS. Okay, and the running time is this. Big O of n cubed over epsilon. Okay, so it's linear in 1 over epsilon, and it's cubic in n. So here's the idea of the algorithm. I'm not going to give you the fully specified algorithm, nor will I show you exactly why it works, but I want to give you the idea of it. So it's based on a DP algorithm. Not ours that we know, but a different one. Based on a DP algorithm. So here's the idea of this DP algorithm. Let's define W of I and V to be the minimum weight of a subset using items 1 through I, a subset of 1 to ... I with value greater than or equal to V. Okay, and so this is kind of a weird object, right? It's hard to see how you can build an algorithm out of this, but essentially what you could do is you could say I can easily calculate an upper bound on the total like value that a knapsack could take. I just take the most valuable item and I multiply that value by n, and there's for sure there's no more subsets. There's no subsets that are more valuable than that. And then what I could do is I could plug that value, that maximum value, in here, and then iterate the following recurrence relation. So here's the recurrence relation that drives this. So W of I and V is equal to the smaller of, and this is for the same reasons that we had this same similar recurrence relation earlier in the class, the smaller of W of I minus 1 in V, right? That says, the best I can do with with I and V is possibly the best I could do without I. Like if I isn't part of this good subset, then removing I doesn't hurt me. And then the other minimum here is the weight of I. I remove item I, and then I subtract its value and weight, right? So I take the weight of the item plus my big W of I minus 1, and the value that I'm plugging in minus the value of item I. Okay, so here's our main recurrence relation that we can use to define this WIV. And if you believe that WIV, that like once I build this whole DP table, the table will contain the optimal answer, you can certainly use this recurrence relation in either a bottom-up or top-down with memoization, approach to find the optimal subset. And so the table that this thing gives looks like this. We have a not particularly tall but extremely wide table. So just like before, I've got n on the way down. And now notice the second entry of my function here is the value of a subset. And so I need my table to be as wide as it needs to be able to capture the highest possible value subset. And we know that the value of any subset is always going to be less than or equal to n times the value of the most valuable item. So value of item 1, where v1 is greater than v2, greater than v3, ... Right? So I'm calling v1 the most valuable item, or 1 the most valuable item. And so n times the value of the most valuable item is the largest the value of any subset could ever be. So the table has n rows and then n times v1 columns. Okay, so it's a very, very, potentially very wide table. And so the overall time complexity then of this algorithm is big O of n squared times v1. All right, and this is pseudo polynomial. And why is that? It's because that's a number. It's not a. I mean, it may be a very large number, which would require a large number of bits. And so this is pseudo polynomial, for the same reason that the other algorithm was pseudo polynomial. So it's not actually a polynomial time algorithm. However, we can use this to make a polynomial time algorithm. And here's the idea. The thing that would slow this algorithm down is if this table is very, very wide. In other words, if v1 is very, very large. So what we do is we say, well, I don't want to search the whole table. So instead, I'm gonna stripe it. So I'm gonna break it down into blocks of columns, and then run my algorithm on these coarser columns rather than on the very fine individual values. So here's the idea of the FPTAS. Break. So I'm going to split this thing. Oh, sorry. Let's see. So I want to chop this thing up into a bunch of columns. Chop table into coarser columns. And for technical reasons, the specific number of columns we're going to choose is n squared divided by epsilon. Okay, so this table then becomes a much coarser table, where now I've got these stripes, these vertical stripes here. So I still have this table being n tall, but now instead of being v1 times n wide, now the width is n squared over epsilon. And so it turns out, and I'm not going to go into any of this detail, but it turns out that you can infer something about the optimality of a solution by looking at a particular cell in this coarse table. Like essentially, the value that you can obtain here is greater than the value you could obtain with something else, and so you can use that to develop your FPTAS bound. I can, if you're interested, contact me and I can give you resources to dig into this more deeply. But this is the gist of the concept. And so you solve this thing like before, and now your time, this table can be searched in time big O of n cubed divided by epsilon. And this is cubic in n, and it's linear in 1 over epsilon, so it is a fully polynomial time approximation scheme.